we have now a tool that allows us to analyze and predict the form of the equation that we should expect to appear in that weakly nonlinear analysis. Well, I'm claiming that. So I gave like a preview of how this will work. So let's now implement it for our half bifurcation. So the idea is that we have a system that has a certain symmetry, and that symmetry induces an action on the amplitude of our analysis. In our case, that is the oscillation amplitude. In other cases, could be some other amplitude, whatever the amplitude is of that eigenvector in that weakly nonlinear analysis. And so we want to deduce then the form of the equation that we get from there. So in general, of course, we said we have always some equation of the form dTA is equal to f of A and A star, because in our case, A is a complex quantity. And we're doing this in an expansion in amplitudes. So we can always write this as a sum over A to the mth power, A star to the nth power. M goes from 0 and n starts from 0 to whatever order we go. And the action that we have in our case, we have that the t going to t plus delta t symmetry induces the action A going to A times e to the I delta phi. Okay, so that means the equation that we have here, this equation, needs to be equivariant under that transformation. So let's apply that transformation. So what do we get? We get the time derivative of A times e to the I delta phi is equal to the sum over A to the mth power, A star to the nth power, and then we get a whole bunch of delta phi's, right? For each power of A, we get a plus, so we have a plus m, and A star transforms the other way around, of course, because it's a complex conjugate, so we have m minus n here. Of course, this thing here, because delta phi is a constant, this is the same as e to the I delta phi dA by dt. And so now we know that not only does A have to satisfy this equation, but it also has to satisfy this equation. And so we have an equation now for dA by dt with two equations, this one and that one. And so if you push the e to the I delta phi to the right-hand side, then you get a condition, which is that on the one hand, let me first write down this term on the left side. So on the one hand, we need that the sum over A to the m, A star to the n equals this stuff, including the e to the I delta phi, which is the sum over A to the m, A star to the n times e to the I delta phi times m minus n, and then from the left-hand side, we get a minus 1. This must be true for all powers of A and A star. And so therefore we conclude, let's emphasize that this needs to be true for all delta phi, right? It's not just for one value of delta phi. We have a continuous term translation symmetry. So any phase shift is allowed. That's important because that implies that each of these factors by themselves, this factor has to be equal to 1, meaning m minus n minus 1 has to be equal to 0. I made a subtle little mistake, oversight. Of course, that powers here is not just these, they're coefficients, a, m, n, right? So I better keep those. So I have here an a, m, n, and similarly an a, m, n. And so now the precise statement is not that m has to be equal to n plus 1, but rather either m is equal to n plus 1, in which case this is 1, and the equation is satisfied, or the coefficient AMN is 0, right? So that's the selection rule, that only those terms can be allowed in the equation, only those AMNs can be non-zero for which this is equal to 0. Okay, so we have the selection rule. There we have either m is equal to n plus 1, or AMN is equal to 0. So that's what we get. So let's see whether that's consistent with what we know from our explicit calculation. So the power of m has to be 1 bigger than n. So that means the terms that are allowed are the following. Let's just write it out. dA by dt. So the lowest order term, right? We start with m equals 0 and n equals 0. So the lowest order term is that n would be equal to 0 and m would be equals to 1. So that would be an A1, 0 times A. Then could be n could be equal to 1, in which case m has to be equal to 2. So we have A21, which is A squared A star, which of course is A absolute value squared A. And in general, so we have A, what did we say? Mn with n plus 1 comma n. And so this is always A times A absolute value squared to the nth power, right? So there's always one factor extra for A, and then there are n factors A and A star. So we've now shown that all terms to all orders have to have this special form that only the absolute value squared shows up in addition to the A. You can think of it, well, it's not really much different, but it's sometimes nicer to say that, the action that we have, we induces, if we have a term A to the M, A star to the N in our equation, then the action of that is, of course, goes A to the M, A star to the N times E to the I delta phi M minus N. And we need to have that all terms in the equation transform the same way. And so since we also always have the equation, always has a dA by dt, which goes to dA by dt times e to the I delta phi, we will have that m minus n has to be equal to 1, right? And so that's what we just came up with. But one can sort of directly just say these guys transform like that. Okay, good. So we now have strongly restricted the terms that can show up. And so now, as I promised, we should be able to deduce what kind of scaling we should pick. And so let's think about that. So we have scaling. Well, I guess in this case, it's actually quite straightforward. So we don't have to write down a lot. So what is going to happen? I'm still thinking completely in a multi-time approach, right? We do our expansions in epsilon and so on and so on. So that means what we aim for is that at some point in the expansion, at some order in epsilon, we will get a solvability condition. And that solvability condition should amount to the equation we're looking for. Well, okay, in principle, there's many solvability conditions, right? So there are some which automatically will be satisfied, so they will not do anything. Excuse me, that in the half bifurcation that was at order epsilon squared, you never get the solvability condition is always satisfied. But if you went to higher orders, at fifth order, there could be a new condition. And in fact, we would expect this because right just now we said, well, there could be higher order terms like an A absolute value squared times A within fifth order term. But we're aiming at the lowest order non-trivial equation, right? And that should contain as much as possible about the system, right? So we want to have all terms that are significant. They are supposed to all show up in the same order. And so let's see. Let me not introduce an epsilon. Let's just look at it. The key element is we know that, well, there always will be a linear term, right? That's obvious because the left-hand side is a dA by dt, and A will always transform the same way as dA by dt. So that's a given. So the only thing we actually have to pay attention to is that here the first nonlinear term is a cubic term. And so unless for some reason A21 was 0 or very small, this would be the term we would focus on. And so that means we would expect, we want to scale things so that our solvability condition shows that it's cubic order in A. And that means this term also has to be a cubic order in A, and so it does that. So we simply have, yeah, like, let's say all relevant terms should be at cubic order. Should be at order A cubed. And so therefore we see that d by dt must be of the order of A. And that's the same as an order of A. No, that's not right. Order A squared, right? We need that this thing here overall has to be order A cubed. So d by dt has to be order A squared, as does this coefficient, which I guess we usually would expect this to be our control parameter. So there could be, I'll just put a mu there as reminding ourselves the bifurcation parameter would show up here, because that's what controls the growth rate, which usually is our control parameter, our bifurcation parameter. And so we have that scaling, and that's actually the scaling we did in our calculations. So this is very nice. Let's see, what's the power, what's the weakness? Well, the power is that we didn't do a lot of work here, right? I mean, if you think about how much algebra we had to do, it was very little. And we predicted the equation that we will get. We predicted the form of the equation. Now, to really predict what's going to happen, we would need to know, in particular, this coefficient, right? If that coefficient has a negative real part, it will be a supercritical bifurcation. If it's positive, it will subcritical, and that will make a big difference. So our analysis does not give us any information about that. So if you really need to know numbers, which sometimes you do, sometimes you don't, then you have to still do that detailed expansion. But we don't have to guess any scaling. We know the scaling that should work. Of course, as I said, it could always be that in the system in question, that this coefficient happens to be 0, in which case, okay, the next term would be the quintic term, we would know what to balance that. But that's just, that would be a coincidence. And so it's not a problem of this approach. Let me mention, though, that there are many situations where you can make predictions without even knowing the numbers. Well, in this case, we actually need to know only the sign. But you still, I mean, even if you don't know the sign, we can show what's possible, right? We know that to cubic order, the only things that are possible are the two scenarios. Either you have a forward supercritical Hopf, or you have a subcritical Hopf. That's, you don't need to do any work to show, any more work to show that. And that can be very powerful. Okay, good. So then we can go on and look at what happens when we actually have forced oscillators. Because they are, well, we'll see how that to deal with. There's a lot of rich behavior that one can extract that way, and we'll use this technique to do that.